So our next speaker is Chuang. Chuang is a faculty member at the UMass Summers, and he's also a research manager at the MIT, IBM, Watson AI Lab. And his research really pushes human-like capabilities of autonomous agents towards reasoning and acting in the physical world. And he also contributed to the Genesis simulator that previously Katrina mentioned. And he graduated with honors from Tsinghua University. And he spent some time as a postdoctoral researcher at MIT. So please, Chuang, the floor is yours.
All right. So thanks for the next introduction. So I'm very excited to be invited to this world model workshop. So today, actually, I will present a recently released stuff. So it actually is a combination of the long-term effort we have been working on called the world simulator. So how many people have seen this actually just posted yesterday? Virtual community, raise your hand. Okay, a little bit. Okay, that's good. So which means that you can learn that from my talk. All right, so let's start to let's start a talk to watch a video of my daughter Karen. So she's playing a popular game called the Circle Puzzle. We could find that she has a basic knowledge about objects and how to interact them. And eventually, she's managed to figure out a plan to finish the task very efficiently. Even though she sometimes to reformulate the plan, but eventually she can make it in a very efficient way. So the question is that why could she succeed in this task? The cognitive study from cognitive side has tried that even the 15-year-old baby here has the knowledge about object, and also the abstract knowledge about object affordance, how to interact with them. And eventually, she can use her mental model to imagine what's going to happen next and plan her action accordingly. Then the most question in our lab have been started, how about the embodied intelligence today, that how we can reach the level of the caring. Then the first question we need to answer is that whether the most advanced embodied intelligent agent has this kind of level plausibility of my daughter caring or not. So you might say yes, because we have seen many powerful robots that, for example, they can help you to unfold clothes, play soccer, help you to clean the room, and even do this kind of fancy treasure and kite game. But I would still say that we don't really have the kind of general embodied agent. So what do I mean by that one? To start with, maybe we can have a rough definition of generalized agent. The definition can be very different, but usually we talk about a robot agent that can take multimodal instruction and perform a wide range of tasks across diverse environments. And then we can see that how about the most, actually last year, one of the most advanced robot system for the robot Aloha can perform that kind of task in terms of generalization. You can see even though they are very powerful in many perspectives, but they are still fail in some easy tasks that actually are trivial for humans. So from this video, we can say that we are still far from having that kind of generalized embodied agent that can interact with the world as flexible as we human. So, but in our lab, we are trying to do that is trying to take another route that by reverse engineering the world model working human brain and building a world simulator to achieve the goal. There's many definitions of world model. For them, in this, people have been talking about world knowledges and world model, has thinking about using this kind of large multimodal model to represent it as a world model. They actually can do some decent job here. For example, you ask these images, so you give these images, ask what will happen next. So they basically can tell that, okay, these images show a hand appearing to drop by egg, and without support, the egg will likely fall due to gravity and may break upon hitting the hard surface. It seems that they have the kind of decent understanding about the object and also physics, right? But how about we take a little bit harder question? But this might also be trivial for everyone. So which ball will reach ground further? So the GPT-4 will answer that they will ground at the same time. But based on our human knowledge, actually we can answer this query very easily because this ball takes a shorter path and has larger acceleration. So apparently this probably will hit the ground earlier, right? And you ask the GPT-4, even he made the wrong mistake, but he can return some fact in a very clear way. For example, he said that there are only 4 icons of ball in gravity, which puts them down within the same acceleration. The time it takes for drive for a certain vertical distance is independent of horizontal distance cover, and then they fall at the same time. So all the facts they are typing is really right, but they just not go out with this scenario here. And there's more more well-known word model simulator. So word simulator definition is using the video model. I think Katerina also talked about this one. They indeed can generate very photorealistic images, but we also know they are not really reliable, that they are making this kind of funny physical mistake. For them in this box only, they can even translate this them clearly learn from, and also this kind of anti-physics video generation behavior. And even we try to do the very basic manipulation task for them. They can custom task, and then the chair just fly away. So yeah, maybe we have more and more data, the model will become better and better. But this still we need to touch the basics that how we can model the kind of field work in a much more accurate way, right? So in our lab, we have been working on the idea called generative simulation. The idea is to basically combine the power of generative AI and differentiable field engine. Let's take a simple example as a question that when you see these images, can anyone tell me that which object is heavier? So how many people think the green sphere is heavier? Raise your hand. How many people think the green sphere? Okay. Now if you raise your hand, it's very confusing, right? But how about I see this video? Okay, tell me, so how many people think the green sphere is heavier? Okay, how do you answer the question? You're basing some physics knowledge of conservation of momentum, right? So the idea of using physics simulation to do that kind of inverse theta is really similar to how we humans solve the problem. So we have building that kind of tool called the differentiable simulation for a while. So the basic idea that given the current state of physical parameter, and then for physical simulation, actually you can do the forward pass, and then you can control the whole physical process. And in this case, actually, you can, so the idea here, we're trying to using a physics simulator to estimate the field parameter, is that you're trying to simulate the object trajectory and trying to see whether your simulate trajectory matching the video result. If they can match, actually means that you estimate the field parameter in an accurate way, right? So the objective function here, you can just minimize the loss by inferring the optimal physical parameter. So this is the reason why we needed to build a differentiable physics simulator. So the idea here, we're trying to make it like a physics equation differentiable, and then you can solve this inverse physics problem by by using gradient descent. It's very similar to you training your neural network. And here example that you take a left-side real-world example, and we can using the kind of different physics engineer to reconstruct the physical parameter and build it like a digital twin in a very accurate way. You may be wondering that how this approach that can generate to much more complex shape. For them, they can do articulated body and even solid body. So the idea here is, besides the differentiable physics engine, we can add another differentiable render engine here. So the idea that we can compare your rendered images and the video observation and to see whether they are matching or not. And then we leveraging the differentiable physics engine and differentiable rendering okay, so the whole inverse physics problem using gradient descent again. So this is a real example that you can take in, So you can take a real world quadrilateral example and reconstruct their control signal in the simulation in an accurate way. And so go beyond that kind of region, we also think about how we can do that kind of system magnification without any geometry prior. For example, we're trying to estimate the Young's modulus of this color and also the viscosity of this droplet. To achieve that, we combine the idea of a neural rendering, that you take multi-view images, you reconstruct both geometry and the physics, in this way, actually, you can reconstruct the physics of that kind of solid body. So you can reconstruct both geometry and the physics of a solid body in a relatively decent way. So how about this kind of world model really related to the robot manipulation? It's more about the core of this workshop. So the idea here is that this differential video engine can not only be using for the system identification, by simply adapt this kind of framework, we can also use that to show the robotic manipulation task. For example, the physics parameter here, we can actually replace with the action. And then with the current system, with the system meter and action, you actually can also control the whole physics process. And since this is a planning task, you can always define a reward function to tell you how well you solve this task, right? And again, the objective then the objective then the training objective has become to maximize the total reward you can earn by choosing an optimal action sequence. Similar to the previous solution, you can also using gradient descent to solve that kind of action optimization problem. We first apply this idea to the solid body manipulation task. So the task here is trying to manipulate an effector and deform the plastic into a desired shape. So traditional approach usually using the reinforced learning to solve this problem, which is actually not very data efficient. In our solution, we propose this kind of gradient-based physics solution. We found that by only using a 200 example, we can optimize a beautiful trajectory in a very flexible way. But for reinforcement learning, even we train for 10K episodes, we are not able to find any suitable solutions. So on the left side, we draw the curve that on the green side, with the green color, you can see that this gradient-based physics solution can earn much more reward than the traditional reinforcement learning algorithm. And you may be curious that how the kind of simulation framework can really generate to the real world, because in the simulation, you always do the kind of open loop trajectory optimization, but in the real world, you're always using the kind of closed loop policy learning. So here, we're always using the kind of neural network so the perspective of using the differential simulation is more like a data engine. We're trying to provide a large and diverse set of downstream data, and then we can using that kind of training the foundation model or whatever the policy model you really want. So we have applied this kind of powerful idea for many different applications. For example, here is a project we done 2 or 3 years ago. So the task here we're trying to do the kind of multi-material cutting task. Basically, we aim to cut as much volume as possible, but to avoid to hitting the middle rigid body core. And we're using different physics engine to optimize the beautiful trajectory here. And then we're learning this kind of closed loop policy, and so that they can actually transfer well in the real world task, that they can cut different sides of the kind of route without colliding with the rigid core in the middle. And Carolina's student has also intended this idea. It's Xianzhou, so he has intended this idea to do the kind of fluid manipulation and transfer to teach robot to make this kind of ice cream and make coffee latte for you. And my student Ian has even intended that kind of framework to do the kind of thin shell contact-rich manipulation, and also the kind of self-tearing locomotion task, and also manipulation task. But this program actually has several problems to really scale up. The first problem that you can see that most of the robot simulation is more like one simulator for one material. We are not really exact that kind of simulator can unify all the effort from rigid body, articulated, solid body, deformable, all the things together. And the second part, even you have a very powerful simulator, you still need to spend tremendous time to figure out what task you want to do. For example, in the behavior, we need to define 1,000 human daily life. And also we need to set up the scene manually. And then we need to humanly writing the kind of reward function to make it learn. So the idea here that is that we're trying to build the kind of generative and unified field simulation. This is the original of the Genesis simulator you met already here. So the idea is that how we build a kind of unified simulator. So this Genesis simulator has came out since last September. I think by yesterday, it reached around 100K. It just reached 100K download. So the idea of genesis is that it supports a large diverse set of object material, including rigid body, liquid, gas material, deformable, thin shell, and granular. So one of the most important is kind of unified simulator, because that is that we implemented them into one unified framework, and also solve most of their coupling material coupling problem. Then, which means that you don't really need to shift the simulator at some time, that you can just use genesis for all the tasks. And we also support a wide range of robots, from robot arm, mobile manipulation, luggage robot, drone, soft robots. So everything actually can do. So everything you want to do about robot, we also can always achieve that in the genesis world. And since the last release, actually, it received big attention. If you haven't downloaded that, okay, try to go to the website and make a try. Even we have this in genesis there, we still need to solve a second question, that how we can enable that kind of automatic skill learning in the simulation. This is the essential how we really can scale up the simulation learning, because many robot people will argue whether the simulation can be useful or not, because they can always teleoperation data that can be much fast to get in policy. But here, but when you're setting a simulation, you need to learn. You also need to actually finding aside the proposed tasks, and also trying to find out the right signal to training the framework. Okay, this seems a little bit tedious. And our idea is how can we automate the whole process? So this is the essential idea of RobotGen. We have been released, I think, 1.5 years ago. So the idea here is that we're trying to using the generative model that can automate proposed tasks, doing the scene generation, as well as generating the training, as well as writing the reward function, objective function, or even select the training algorithm. And then everything actually can be automated learning simulation with little human intervention. So let's take example that we give this kind of robot arm and the object safe. We can actually ask a larger model, okay, what can you do with this robot and this safe? He actually gave an answer that you can actually open the safe door, or you can retrieve one gold bar and lock the safe. So based on this kind of language description, we can then generate the scene. So basically, you can we can retrieve the relevant assets from almost 3 library and define the asset size based on the knowledge in the larger model or world model, and then we can define the scene configuration and also how we put the scene. For every asset, we can either using the existing asset, or we can using some type of 3D model to choose that one. And another perspective we find very important is doing this kind of idea of test time scaling. So basically, you're using a verifier to verify. So basically, generate a bunch of different scenes. You're using VLM as a verifier to verify to select which scene actually can be best valid for a task. With all this scene population, the last step that you're trying to do the skill learning, and this is a principal part for always for human. Okay, whether we're using task motion planning, how we can decompose the task, or even we can training how we can design the reward function. But this part actually can be always automated using the generative model. For example, we can use LM to write a reward function. We can use LM to decompose tasks. And later, I will also tell you how we can, in some challenging tasks, how we can using a video model to define the goal and the reward function and enable all the robot skill learning automatically in the simulation. This is our mission. As a result, that we have making that kind of so that kind of automated skill, that basically give robot give a task that all the robot skill learning can be automatically happen in the simulation. You can find using that we can learning a large range of diverse skills, including locomotion, manipulation, data manipulation, mobile manipulation. So everything happen is automated in the simulation. So essentially, when we talk about the agent everywhere, actually what we hope to get, we have a kind of generative robotic agent that can automatically propose new tasks. Teach them have no skill, and all the process should be endless and automated. And in this framework, actually, we found 2 challenging for the next step. First, that for writing the training signal, people always using the kind of LM. Actually, LM don't really have too much information for them to take the soft body material. So it's usually hard to generate the goal for deformed object. And also, we find that the robot body is also, in sometimes also limitation that, for example, in some manipulation tasks, the robot greater might not be enough to solve all the tasks. And to solve the first problem in our recent work that we called the Lucy bot, the idea that we're trying to using a video model to do the goal generation, for example, given the task. So we're trying to learning from this kind of generative video, for example, how human pouring the water, how human actually pick up a spoon and go a sponsor stand, or even pick up the knife and cut the dove. Using the video, actually, we can actually taking the video and training a perception model to basically guiding the trajectory, and then we're using some trajectory optimization. So basically, we take the human initial so we take the human trajectory as the initial trajectory for robot policy, and then we can refine the policy using the differential physics engine. So this is the high-level idea. So as a result, we are able to teach robot to a bunch of very diverse deformable object manipulation tasks. And now actually we learn we get the training signal from generative video. In the second part, actually, we also think that for robot manipulation tasks, that for human so many tasks that you need to have some tool here. And the last effort actually is also human-defined tool. And our idea that whether we can use the kind of generative simulation idea, can using LM, basically they can for them give a user what task they want to do. So basically can use LM to generate the tool. And then you have another VRM doing the multi-agent system. They can evaluate the thing whether the tool can solve the task or not. Then you can revise the tool size. And eventually you can do job optimization of the kind of tool design as well as the policy learning. Here I want to show some real world results. For example, here we are designing that here actually we want to pouring the water into this small size of the bottle. Actually, if you just put in the bottle here, it's very hard. But we design that kind of tool here that the robot can do the task in a much flexible and easy way. And we also taking this, we also making that kind of pizza example that we're trying to make a tool that how we can put in salt in this kind of small pool and making the pizza for you. All right, so in the second part of the talk, actually, we mostly talk about our mission that how many people has watched the video of Dash Race Become Human? Raise your hand. Okay, not that much. So basically, we are telling a story how human and robot can co-evolve in the social world. So as we all know that the robot will probably be everywhere in the next few years. And the embodied intelligence should not only about interact with the physical world, because the most important perspective in the world actually is human. So in the next year, we have been thinking about the following problem that when robots become everywhere today, how we can deal with because they probably will share the same community with us. We need to figure out how robots can intelligently cooperate and even sometimes they are compete. And how humans develop kind of social relationship and build community with agents. And most important, fundamentally, how we can deal with them that both coexist in our open world. So this goal actually we call as embodied physical and social intelligence. We need to build a robot that can interact with the physical world, but as well as with other intelligent beings. This is called embodied physical and social intelligence. And to achieve that, actually we need a unified world simulator that can support the simulation of robot, human, and also their communities. How can we be there? So this is the essential idea. So this is the essential motivation for our virtual community project. So this virtual community is really about an open world for robot, human, and society, how they can collaborate, coevolve, and grow together. So basically, the virtual community built on top of Genesis, which means that they inherit most of the robot simulation capabilities from Genesis. But we make two innovations here. That the first part, we're trying to building a unified simulation for both human and robot. So so this is this actually makes Genesis to be an optimal choice for us. So you probably have to see a lot of that kind of human interest, so human avatar example. But we have to say most of them actually building on the game engine for the Unity or even Unreal. The problem of this one, they are not really designed for robotics. So that's why we take a reverse path. That instead of building a Unity and Unreal, actually we build from a robot simulator, and then we add human and robot interaction on top of them. So that's the what direction we choose. And another idea that we think most of robot learning right now is really happen in either in indoor environment or in some the kind of game human created environment. But actually, we really need the robot and human coexist in the real world scenario. All the study really need to get in the real world geometry data. So this is a big effort we have trying to reproduce the world anywhere. So basically, we can take the Google Map, select the location, coordinate, altitude, and we can using the Google View images and also the 3D tile data, basically trying to reconstruct the world everywhere. And then we populate the agent and building a bunch of tasks in the real world scenario. So this is the real mission of virtual community. Scale up robot and human learning in real world scenario. And as a result, that we can generate so basically we can take we can take anywhere in the world, give us the city. Actually, we can reconstruct the city scenario here, and then we can populate agent based on the kind of generate this thing. So so actually we leveraging the kind of 3D and 2D data as well as the map data, and we start from the 3D pile data, the Google pile data, but it's well known it's not really that kind of simulation ready to use. It's not that kind of clean, and also their mesh geometry not correct. So we actually propose that kind of geometry simplification of the building, and then we doing the kind of precision masking some noisy actor using perception model to detect some object, for example, the car, the vehicle, human, and remove them out. We're also using the generative model such as stable diffusion to implement the texture. To basically to generate the kind of relatively photorealistic real-world scene at scale. And that actually we actually building the kind of scene-grounded agent that basically we also have the kind of well-known character, LM mask, all the people here based on we use LM to design their profile, and then we think about how they will interact with the agent. Eventually, we are building that kind of large-scale physical and social interaction happen in real world, including a political campaign, the kind of a robot following the child, or even the kind of offensive or assaulting task. And also it's happening everywhere in the world, from London, New York, Park, so we can always simulate the real world scene and define the activity beyond here. All right, so I'm going to summarize my talk. So I've been asking that what's the long-term vision of the Genesis stuff. So basically, we're always thinking that the Genesis could be considered the next generation of the linear kernel for embodied AI. And we see there will be a large, there will be two-step effort we are trying to working on. So the first thing we call is called Genesis build. Essentially, it's a large-scale synthetic robotic data generation pipeline. We are working on releasing a super large robot manipulation demonstration data set and also evaluate benchmark that is for all the robotic community can training foundation model as well as doing the model evaluation in simulation at scale. On the second part, we are working on building the kind of on-device 3D embodied foundation model. So basically, we're thinking that a lot of robot power learning right now happen on the 2D. It's obvious that in many cases, even as Karina will show you, that a lot of things working on 3D or even 4D can be much simpler and the policy can be much easier to generate. But the problem is that we don't really have data. And Genesis provides the kind of simulation actually is all the 3D, 4D data came as free. So this actually offers us an opportunity to build in the kind of 3D-based or 4D-based embodied world foundation model. And we are also thinking that to connect with the foundation model with symbolic program and feed engine. So the idea that you have already seen some idea about using language to control the physics engine in the Genesis demo. So basically, we are thinking to building another cursor version of the physics engine. So basically, the ultimate goal is we're trying to remove the barrier for people using the physics simulation. We hope everyone can just use their language, can simulate the scene. So basically, it's more like using the ChatGPT, you put your query, it can edit the scene, and generate a site, generate the training signal, everything that you can use in language to interact with Genesis to achieve robot learning at scale. All right, so this is all my talk. I'm happy to take any question. Thank you.
Okay, thank you, Chuang. Again, while the next speaker sets up, do you have any question to ask? And thank you for the great presentation, by the way. Kami.
Thanks for the talk. I'm curious how you decided on choosing the Genesis simulator, and what's your experience using other simulators, and what's your decision process for that?
Okay, so the question is that how can we compare with Genesis and other simulation? Is my understanding correct?
Or more so about how you decided on choosing Genesis and your specific requirements in making that decision.
Okay. So let me share a little bit story about building my roadmap to building the world simulator. So how many people had heard of a simulator called 3D World? Raise your hand. Not that much. Okay. This is actually the first simulator I have built since 2017, when I was the first day at 2018. The first day I'm being a postdoc at MIT. So the idea of 3D World is building. Actually, at that time, a lot of robot simulator building on top of the Unity of the kind of game engine. So the idea that we really want to have so because before people most using the kind of robot simulator, it's really about physics, not really about the photorealistic rendering. And from computer vision community, people always thinking that we need both good physics and also good rendering qualities. So this is essentially Unity and Unreal, this kind of game engine become an automatic choice to doing that one, because they basically couple good. So basic game engine very aligned with the purpose of the kind of robot simulator, that you can have good physics and good rendering. I have been working on the 3D World. So this is essential how we build in 3D World, and also some Habitat, virtual community, or even the Sapien all built on this idea. But we have been working on this kind of 3 or 4 years that we never get it popular and be very easy to use. One of the reasons that the kind of Unity and Unreal is most designed for game, not for robotics. And a lot of time, actually, we spend time is mostly on fixing bugs on Unity and Unreal. And people, and also you probably Unity and Unreal, actually, they are not using Python. That's the most popular language to write. So you have to go into the low level to keep debugging. This idea that we're thinking, okay, why? And also, the Unreal field is not really doing for anything about robot. It's not easy to put a robot body in the simulator at all. At that time, we are thinking, okay, we have to build something from scratch. And that time, I think like 2021, 22, I don't remember exactly. And Yuan Ming actually told me, okay, I'm building a compiler called Tai Chi. And he's most from computer graphics community. And he writes the last paper at MIT with me, is actually the pricing lab. We see the opportunity that we can use in the kind of differentiable simulator, the kind of programming, to really write so that kind of robot simulator from scratch. And then the story that I met Xianzhou, actually Karina's student, he's willing to take the lead and actually to build a kind of unified Genesis simulator from scratch with full control. And the most important thing, makes it fully open source. So I can see this is more like a cycle that is more like, for example, DeepSeek, we essentially put all the language model trained to be open source, and Genesis also want to do the same. If you're using the SLG or some other, you probably see that a lot of simulators are not really open source in there. Even Matterworth, SFG, they are not really open in the low level, but the Genesis actually open everything. Essentially, I think I hear that last week, SFG also decided to open everything, so this actually a good cycle for everything. So I honestly don't know who will be the winner, and also I don't think we need to know who is the winner, but the thing that we really need to build in this kind of ecosystem to push robot simulation can be widely used. Everyone can contribute, and also everyone can be easy to use. This is my mission. All right.
Let's thank again our speaker then.